Hello everyone. So today I would like to show you some recent work on oscillation in quiescent solar prominence. As you can see, this work is in collaboration with many co-authors from the different institutions, and it's still ongoing work, so these results are kind of preliminary, but we are hoping to publish this year. So first, I would like to remind you what are the solar prominences. So solar prominences, they also may have been called filaments when they are seen projected on the solar disk, are cool and dense and complex plasma structures sustained by the intricate topology of coronal magnetic fields. And they are observed in hot, tenuous solar corona, often destabilized, eventually erupting as coronal mass ejections. And for over 2 decades, there was many different classifications of the solar prominences introduced. However, today I would like to focus on the most popular one classification, which based on the evolution of the prominences. So the first type will be the quiescent prominences, and they are like magnetized, relatively cool and dense materials. They are formed about 35 to 50,000 kilometers above the solar surface. And these are having like a non-eruptive state. They are just small, calm, compared to the other type, which are eruptive prominences, and those are a little bit hotter, but still relatively cool compared to the background corona. And what is characteristic for them, it's rapid upward plasma acceleration from velocities from 100 kilometers per second up to even 1000 kilometers per second, and it's very rapid in time. It can be in the matters of, I don't know, 2-3 hours even. So these ones developed very frequently into CMEs. And then we have the third type, and these are coronal clouds. And these are cool materials suspended up to 200,000 kilometers in the corona, and they have also V-shaped structure. Sometimes they are called also coronal spiders, and what is characteristic for them, they do not erupt. And here I have for you like 2 examples. So the first example is the measurement taken by our comp at the LSO observatory, and this is eruptive prominence, and above and this is in H alpha line, and above you can see the quiescent prominence that I will be talking about, taken by the Solar Dynamics Observatory at 304 line. Okay, and we are very lucky because we can measure the sun using spaceborne solar observatories, and specifically the prominences can be measured in helium-2 single ionized helium line, which is which is at a 304 angstrom. And basically what we can see in this line, so the plasma at the 304 is optically thick, so it means that we are probing only the shallow layers of the prominence, so we are not going very deep inside. So basically what we see here is the radiation from the outer part of the prominence. So also thanks to the many different observatories which are in space, we can observe the sun simultaneously with the different spacecrafts, and luckily this time 2 of the spacecraft were observing the sun at the same time, and they were in the opposition. And one of them was stereo A, giving us the ahead view of the sun, and our prominence is here. And the second was the solar orbiter on the other side of the Sun which was observing the same feature from behind. So this can give us like kind of stereoscopic view on this prominence. So stereo A is a instrument which is observing not only, but we are using observations in extreme ultraviolet imager in the 304 line, and we have this ahead view whereas the solar orbiter is the full sun imager and also ultraviolet imager in the 304 channel, and it gives us the beautiful behind view of the same features. So as you can see, this is the full daytime series of the sun, and it also rotates, so you can see how complicated can be analyzing of this. Of course, we have also the different spacecraft or different observatories that are observing the sun from the space, and the quiescent prominence from space observatories will be discussed in my second part of this talk, which will be probably next semester. But I wanted to show you already that how different can be the view from the same feature at different wavelengths. So basically, 304 is probing very shallow layers, whereas in a different wavelengths like 211 or 171 angstrom, you are probing totally different depths and different temperatures of the solar prominence. Okay, so today I will focus more on the measurements taken by the ground-based instrument. So a solar dynamics Doppler imager, SDDI, mounted at the SMART telescope in Japan, does the imaging spectroscopy of the full disk in H alpha. So Ichimoto et al. 2024 published already some results on this measurement. So basically what they measured the full disk sun, and they observed some prominence showing up in their data. What is the advantage of imaging spectroscopy is actually that we not only have the images of the sun, like a time series of the images, but we also have full spectral profile. So from that, we can calculate then Doppler velocities. So from the intensity, we can shift to the Doppler velocities, which is looking quite different, as you can see here. And this was already published in 2024. So right now we would like to kind of improve these results, and also there were some limitations that we would like to kind of cross-check and examine. But first I will talk more general. What are the oscillations that can be recognized in the prominences in general? So there were, at some point, they will find out that there are types of different kind of oscillations. So one are the winking filaments, and they have velocities about 20 kilometers per second. So the other type of the oscillations that can be detected in the prominences are transverse. So these are like more sideways swing motion of the filament threads, and wide range of oscillatory periods was identified by the work of many persons in the past. So we can have the short period oscillations, and the short period oscillations are smaller than 10 minutes. So they are basically up to 10 minutes. They are very rapid, I would say, in that case. Then we have intermediate periods, which are ranging from 10 minutes to 40 minutes. So this is this range. And then we have long periods, which can be much larger than even 40 minutes. So to register this kind of observations, we would like to have really long time series to catch these ones. So our time series that we have from the Ichimoto is about 3.5 hours. So it's not really long to register like super long period oscillations, but you will see the results in a minute. And past detection of small amplitude oscillations in prominences was reported by many authors, and I wanted to focus on the H-alpha measurements, basically. So H-alpha was ranging with the periods of 3.5 minutes up to even 8 minutes, but the amplitudes was about 2 kilometers per second up to 3.5 kilometers per second, sometimes even less, like 1 kilometer per second. So different results for the different instruments over the time. So what our previous authors did on this quiescent prominence. So basically they analyzed the intensity and the Doppler data. So they derived the velocities, but only in the small part of this prominence. So basically they did like two cuts, vertical and horizontal cut through this prominence, and they were investigating the oscillations there. So they derived the Fourier spectra, which should show us, so this is basically a K omega or L nu diagram, which should derive as the enhancement of the powers at some frequencies. They are the most significant ones. So they found out like the speeds of 10 kilometers per second and about 100 kilometers per second. And actually this is the same diagram but plotted differently. So they observed some power enhancement in 3.5 up to 5 millihertz and around 1 millihertz. Then they also measured, using different instruments, they were also measured polarimetry at the slit measurements using helium-1 line at 1038. And then they had polarimetric intensity and then polarimetric signal for so this is this cut, they were measured by DST. So they did also some kind of pre-analysis of the magnetic field strength, of the intensity and the velocity. And the velocity is about 4 kilometers per second here, so this is called this way. Plus they also give some context image from the space instrument, so this is from the AIA 193 angstrom, and they discovered, based on the slit measurement, that they discovered velocities with 140 kilometers per second, and that actually the plasma is going in one part of this prominence is going to the right, and in the other part of this prominence, so like here, is going to the other side. So this is like very interesting results, but this should actually, this is the same diagram as this one, and it should actually correspond. So we can see that you know, this measurement was like kind of spatially better resolved. So we can see that the spatial resolution matters here. So they identified these periods based on the DST slit measurements. So 910 seconds is about 15 minutes, and then you have 4-minute periods. So what we did, we wanted to cross-check these measurements, and we really struggled with that. So first what I did, I was using 3D wavelet method. So basically wavelet is similar to the Fourier transform, but it uses more discrete functions, and it also gives us the possibility to check the periods within the time. So not only we are kind of averaging over the dominant frequencies, but we also can track the period inside some feature within the time. So I repeat the Ichimoto's results from the Fourier transform. Well, we don't see such a enhancement as they observed. So maybe there is some lack in the description how they construct their diagrams, because usually it should be visible. And I also, so this is the Fourier transform in a form of the L nu diagrams for our prominence in the same location as Ichimoto did. Then I construct also cross spectrum of the intensity and velocity signal. What it gives us is just enhance the signal in the most dominant frequencies. So to reduce the noise and increase the signal, we are using usually cross spectra. And I also checked the coherence, so where these oscillations are coherent. So basically 0 is like there is no coherency, and 1, they are highly coherent. So you can see that there is some small regions where we can really think that this measurement or these results might be true, but this is like really, I would say, not significant too much to have such an interpretation that we have like really 100 kilometers per second in the prominence. So, and yeah, so the 4 minutes actually would be, on our LNU diagram, would be at about 4 millihertz. So this is actually 4.60 millihertz. And the 15 minutes that Ichimoto identified, we can see it also in our, through the whole time series in our wavelet, but it will be lying right there. So for there, it will be somewhere over here, I guess. So I'm not sure about these results, but let's go further. Let's use wavelet, because wavelet seems to be more accurate in this case. So I calculated this kind of wavelet for whole field of view. So I basically use the 3D approach, where I can distinguish between different periods and where are they located. So as we can see, we have different frequency bands, and this is 1 to 3 minutes. Then you have 3 to 5 minutes, 8 to 9, and then finally this 15 minutes, which I'm ranging like 14 to 60 minutes. But as you can see, the power here is like, so the scale can be adjusted to see more, because most of these oscillations are very weak. So to make it more significant, yeah, so here you can see this, what we have on the wavelet, and how it corresponds to the power maps. But when we actually make our scale more significant, we can see that this 1 to 3 minutes are not very present in the prominence body. Same for the 3 to 5 minutes. So Ichimoto said that this 4th minute, that this 4th minute oscillations can be found as a result of some external triggers, but maybe this is true, it's not really confirmed. Although 15 minutes oscillations are present in the whole prominence body. So I need to speed up because Natalia already showed me that I don't have time. Okay, so this is our cube that I calculated, and then I just selected interesting periods. So we just concentrate on the 14 to 16 minutes. And you can see how it varies in time. So basically I selected some loop. It doesn't mean that this is the coronal magnetic loop. It's not. It's just my selection that it might be probable that plasma will be following this path. But this was just like a, naive assumption that it might be like this. But actually, we can see on the time series that the 15 minutes oscillations are kind of increasing in this area. I'm sorry that you cannot see really this loop here, but it's there. So when we went further and tried to kind of plot it, so how it looks like in time. So we have the intensity plots, and we found that the plasma is kind of entering this loop with the velocities of from 600 meters per second up to 1023 meters per second. So this is not the same speed as Ichimoto identified. Moreover, on the other diagram, so we have the Dopplerograms here, and I also did like some kind of slit cuts. So on the slit cuts, you can definitely see some horizontal displacement and like kind of wavy motion on this part of the prominence, but also the velocities are ranging only from 300 most like around 300 meters per second. So why there is such a discrepancy, I have no idea, to be honest. It should be roughly the same, but maybe just the techniques that are used just are different that they were using. And what I am see here, so here I have also still stereo plot intensity. So this is this spaceborne observatory measurement. But I would like to focus today on this plot. So we observe the Doppler velocities in the first loop. So we have the first loop, and here you can see some periodicity of the 30 minutes. So we have 30 minutes in our wavelet plot. So now we can localize them. So basically the 30 minutes oscillations is present, as you can see around here. So this is this part of this loop. So it means that the oscillations that we are detecting might be just present only very near to the solar surface or in transition region. It's very, very low in the solar corona. So this is like interesting result. And moreover, I also plotted our wavelets here. So as you can see that this 15 minutes, this is 15 minutes range of oscillations, so that these 15 minutes are kind of entering this loop. So this is the plot along this loop. And on the other selection, we can see also that they are really entering the central part of the loop. So something is going on there. They might be present in the loops that I selected, but we are not sure about the interpretation yet, how to interpret this. Okay, so summarizing, so based on the wavelet power spectra, we found the oscillations inside the prominence body ranging from 4 to 64 minutes. However, not all of them are significant that might be taken into account. Then inflows velocities inside the selected loop, we found from 200 meters per second up to 1 kilometer, basically, per second. And then horizontal movement of the plasma inside the prominence body, ranging in velocities from about 200-300 meters per second. Now, in the Fourier power spectra, we find dominant frequencies below 1 millihertz and from 2 to 4 millihertz. So this is this might correspond to the Ichimoto results, but to be honest, I am not sure about that. Then we confirm that the 15 minutes oscillations propagate mainly in the prominence body. So this is true. So we know they are inside of the prominence. So maybe we can then somehow use it in the later on. But the 4 minutes are really present only near to the surface. So maybe this oscillations range is triggered by something, but again, we would need more measurement like that to really confirm that. And in fact, 50 minutes oscillations propagate along the loop. And in case of this prominence, so we identified that the dominant oscillations are having the intermediate periods. So, okay, thank you very much. So this was all what I wanted to show you, and I'm open for your questions.
Thank you very much.
I have just a comment. So
yeah.
Thanks for your talk. It's a great, huge work. So I wish you success. Just I want to ask about the Ichimoto's work. You show the horizontal cut in the STO. Yeah.
Yes.
The last one.
This one, yes.
So did they do also the horizontal one? Because on the telescope they did it. Yes.
Yes, this is the horizontal one. And here you have intensity from this cut.
So they did it also the vertical cut?
Yes, you have the vertical and the horizontal one. Yes.
Did they do this vertical cut in SDO? Or?
No, I don't think so. No. In SDO you can see only here. Yes. So I feel that also that is lacking some information in this paper. Actually, a lot, because also in the case of the LMU diagrams, they did not show like the significance of these plots. So basically, you have to do like if you have an access to the Doppler velocities, then you need to do like a cross spectra to improve your significance on this result. You know. So I have To be honest, I have no idea how they achieved such a good signal here. This is like a question, but maybe I should ask them. Yeah.
Thank you very much.
Thank you.